Terrific. Welcome everybody to today's webinar on forest carbon dynamics with William VanDoren from the Massachusetts Department of Conservation and Recreation Forestry Department. He's going to be talking to you about trees and carbon and how they work together. Thanks so much for being here today. And take it away, William.
All right, well, thank you very much. I'm going to go ahead and start my screen sharing. And all right, does that look good? Can you see my first slide?
I can see your first slide.
Great. All right, so I'll turn off my video feed and well, thank you very much for the opportunity to speak to you this afternoon. My name's Bill VanDoren, as Britta said. I work as a forest biometrician for the State Forest and Park System called the Bureau of Forestry within the Massachusetts Department of Conservation and Recreation. And today I'll be discussing forest carbon, including a brief overview of the carbon cycle in forests, including ecosystem and harvested wood product carbon, measuring forest carbon, especially in trees, factors affecting forest carbon stocks at the tree, stand, and landscape scale, and forest carbon in the context of other ecosystem services. So just as a bit of background about myself and career, I was born and raised in southeastern Connecticut, and since my home state university didn't offer a forestry program anymore, I earned my bachelor's degree in forestry at UMass Amherst in 2003. I worked for 5 years as a procurement forester for what was at the time Massachusetts' largest hardwood sawmill in Chesterfield, and this gave me really valuable information and experience in wood products utilization and following forestry from forest growth in the woods all the way through to wood products. The mill went out of business and I turned to consulting work, doing geospatial forestry and other modeling work while earning my master's degree again from UMass in 2012. After that, I worked as a lead biometrician for a firm that developed forest carbon offset projects and due diligence for timberland investors, modeling trees, forest growth and yield, and forest economics. Then in 2018, I came to work for the state doing very similar work, assisting with sampling projects, modeling forest growth and yield, and working for our forest, our carbon and climate goals. A forestry degree is required to practice forestry in the Commonwealth, and the easiest path to licensure is a degree from a university with a major in forestry that's accredited by the Society of American Foresters along with experience. Licensure is primarily a mechanism for consumer and environmental protection when working with forest landowners, developing forest management plans, and implementing forest management and timber harvesting projects. There are alternative paths to licensure that include degrees from non-accredited universities, while also completing a small amount of coursework, usually as independent studies at an accredited college to fill in core requirements like silviculture. So let's start out by taking a big picture look at carbon in forests and forest products. I think this will lead naturally into a discussion of different pools or places where carbon resides in the cycle. So I realize this slide looks complicated, but let's start out with a division between the top and the bottom of this cycle. Forest carbon can reside in the ecosystem, in the woods and natural environment above the solid black line, and in harvested wood products like lumber or paper below. So let's start with ecosystem carbon first. Starting with photosynthesis, plants take energy from the sun, and with carbon dioxide in the air and water translocated by the plant from the soil, they produce stored energy in carbohydrates, and the plant uses this stored energy in maintenance respiration to survive and to grow as well. Respiration breaks down those carbohydrates with oxygen, releasing energy, carbon dioxide, and water. So plants, trees, shrubs, vines, grasses, forbs, herbs, move those starches around in their bodies and grow in pools called the above ground and below ground live parts of these life form classification. As those live trees die, the carbon in them transitions from the live tree and plant pool to the standing dead and down dead pools. The down dead pool is broken into coarse woody material, pieces larger than 3 inches in diameter, and fine woody material, pieces below that threshold. The forest floor includes litter, freshly fallen, mostly non-woody debris that's still recognizable as particular pieces, and duff, a layer of more decomposed organic matter that's also called the O horizon of forest soils. Mechanical damage like wind, lightning, or woodpeckers, and decomposers like fungi and microbes work to break down the dead wood and return nutrients, including carbon, to the soil, while also respiring carbon dioxide. Some of that carbon is held very tightly in inorganic and organic soil carbon, and some can be lost by leaching to stream flow and groundwater or to erosion. Some of the wood that grows in trees may also be harvested and removed from the forest. The dominant part of the tree that's removed is the main stem, which is also called the bole, but in some types of operations, the branches are removed as well. The main stem is sent to a mill or processing facility as what's called industrial roundwood. As that raw, round piece of wood is turned into boards and end products, parts of it, like slabs, edging, the kerf that's cut by a saw blade, those are turned into byproducts like chips and sawdust. Sometimes these products simply decompose, and sometimes they're burned or otherwise oxidized with energy recapture that turns some of that energy into heat and power. The wood fiber in the end products like paper, cabinets, furniture, flooring, insulation, and the cellulose remains in use and gradually decays and is sometimes recycled as well. A really important thing to remember about this cycle is that as long as forest land remains forest land and isn't converted to other uses, it's a closed loop cycle. Harvesting wood products only adds benefits by storing carbon in wood that would otherwise decay and allows for compounding benefits over long periods of time. Keeping forest land as forest land is the #1 thing that can be done to maintain the contribution of forests to the carbon cycle. Converting forest land to other uses, deforestation, breaks that loop. When forest land is converted, like to parking lots, not only does the land lose much of the carbon stocks on it, but it also loses much of its capacity to pull carbon out of the atmosphere. So we've talked about the cycle and started to name some of the pools where forest carbon can reside, but let's start to look at the relative distribution of carbon in these pools. So here we've got graphs that show the different pools, the tons of carbon per acre on average, and the relative proportion of all the carbon in the forest. So on average for forest land in Massachusetts, there's about as much carbon in the top 20 centimeters or 8 inches of mineral forest soil as there is in the above ground and below ground parts of live trees. The next biggest pool is the forest floor that includes the litter and the duff. All classes of dead and down woody material together compose about 2% of the stocks. Larger classes of material have more carbon than the smaller classes. Standing dead trees compose about 1% of forest carbon, which is a bit more than the shrub and understory component. These patterns can vary a little bit by forest type though. The exact magnitude and proportion of pool sizes isn't as important here as looking at the broad trends between hardwood types, common in Massachusetts on the left, and softwood dominated types on the right. Softwood types tend to have proportionally greater forest floor, the duff and litter layers, than hardwood types. Part of this might be attributed to the different nutrient composition of the needles as compared to broadleaves. Part of it might also be attributed to ecological niche, where softwoods often occur on less productive sites with shorter growing seasons. So trees tend to be of smaller stature and decomposition occurs more slowly. And finally, these data shown here are based on empirical observations of forests as they exist now. So they bear the legacy of any past management. They aren't really a statement of what the potential distribution of carbon in a forest type might be under different management regimes. So since forests occur over very broad areas, what we typically do is sample. We measure small numbers of trees to estimate population parameters. To make sure we have a sample that covers the entire area and is proportional to other attributes of the land, like elevation, slope, forest type, ownership, and for reasons of efficiency with fieldwork, we systematically select points for sampling, usually on a square or rectangular grid, like shown here, or sometimes within a hexagonal framework as well. So this helps make sure that the sample is distributed across the land base evenly, rather than potentially clumped due to random chance in one part or another of the sampling area. There might be other types of purposive studies where we only want to sample a very specific microsite or one stand. These types of studies are different, but still equally important in painting a complete picture of our forests at different scales. It's also important to remember that definitions are very important so we have consistency among staff and over time. Also, repeated measurements at the same points in the landscape and of the same trees and vegetation allow for greater statistical power when making estimates of change over time. So at each sample location, we'll install a plot at which we select vegetation for sampling. A variety of sampling types and so plot designs might be used. Let's first start with trees. Most of the biomass in trees is in the main stem, which looks an awful lot like a cylinder. The volume of a cylinder is proportional to the square of its diameter and its height. So tree diameter is the most important variable you can measure to predict volume, biomass, and carbon, and height the second most important. Selecting trees proportional to their diameter would be more statistically efficient. We'd need less effort or samples for a given precision than sampling proportional to their frequency, but both methods have other strengths and weaknesses for long-term plots. The vast majority of strategic long-term sampling programs use fixed radius plots that select trees proportional to their frequency, and we measure the same trees periodically, like every 7 or 10 years. Shrubs and herbaceous vegetation are often either tallied in terms of the number of stems in a fixed area plot and their size, like diameter at root collar, and height are measured, or the percent cover and height established within fixed area plots along linear transects. Downwoody material is divided into coarse woody material, greater than or equal to 3 inches in diameter, 3 size classes of fine woody material, less than 1/4 inch, 1/4 to 1 inch, and 1 inch to 3 inches in diameter. Litter includes intact pieces of fallen leaves and stems resting on top of the forest floor. Duff is essentially the O horizon of the soil profile, decayed organic material so that the individual pieces aren't recognizable anymore. On the coarse and fine woody material, the piece diameter, species, and stage of decay are measured, along with whether the piece is hollow and sometimes length, depending on the needs of the inventory. The depth of the duff and litter layer is also measured. Soil samples can also be collected to be processed for things like texture and organic fraction in nutrients like nitrogen, phosphorus, and potassium, and organic and inorganic carbon. Bulk density can also not only help assess soil compaction, but also helps relate nutrient concentrations to masses. On the other side of the forest carbon cycle, tracking harvested wood products relies on an understanding of tree quality, allometry, and the supply chain. Not all trees are suitable for uses. Some are the wrong species, some are too crooked, too rotten, or too branchy. For every ton of carbon in the above and below ground parts of trees in Massachusetts woods, only about 88% is in trees of good enough quality or size to be used in different manufacturing processes. About 47.8% of carbon in suitable trees, or 42% of carbon in all trees, is in the wood in the main stem or the bole of that tree, which is the part most commonly used. And finally, about 68.6% of the carbon in wood that's brought to the mill makes it into usable products, or 25.6% of all the carbon in live trees. As logs are sawn into boards, saw blades turn solid wood into sawdust, round edges are sawn off to turn round logs into square boards, and raw green lumber, for example, is sold oversized to allow for variation in sawing, shrinkage, and defects as the moisture is driven out of the wood during drying, and planing and surfacing to smooth the wood to its finished appearance. The wood that's harvested and processed winds up in different materials, each of which has characteristic patterns of usage over time. For example, softwood dimension lumber here at the bottom of the graph, used in wood framing construction, has a different pattern of usage over 100 years than does the hardwood lumber that's used in finish carpentry and flooring, than does paper here in the purple part of the graph. As each of those products created from wood reaches the end of its useful life, the products are disposed of. Houses are demolished, furniture and cabinets and flooring are thrown out. The carbon in the wood fiber then either decomposes and the carbon is emitted back out to the atmosphere, or it's burned and emitted with energy recapture where the heat or power are put to some use. So this graph here shows average results from harvested wood in Massachusetts, given our patterns of forest stocking and distribution of wood in different sizes and species of trees. At present, about 60% of our harvested wood that reaches a sawmill results in carbon that's stored in wood products that same year, year zero. 100 years later, about 30% of that carbon is still stored and in use. Another 35%, right here, has been emitted to the atmosphere with some kind of energy recapture, and another 35% or so has been emitted without energy recapture. Larger, better quality trees tend to result in logs from which longer lived wood products can be produced, keeping more of that carbon out of the atmosphere for longer. New research is constantly helping to develop more efficient production processes and products that can store carbon from poorer and poorer quality trees for longer and longer. So we've talked a little bit about forest carbon at a high level, where it's stored in the forest and in wood and its relative proportions. Above ground, since trees are the dominant pool for forest carbon and most easily influenced, let's focus on getting from trees to carbon. At the core of all the estimation methods, we're interested mostly in tree dry biomass, which is approximately 50% carbon. Carbon can also be expressed in different units: pounds, short tons, metric tons. To make things even more confusing, carbon can also be expressed as elemental carbon, or through the joy of stoichiometry, as carbon dioxide equivalent, which is relevant when we're considering carbon in the context of greenhouse gases. But just what does that mean? How much carbon or carbon dioxide equivalent is in a tree? I think the best way is to work through some different models, and models are what we use. There are nearly 1.5 billion trees on forest land in Massachusetts, and in order to measure the carbon in them, we would need to use destructive sampling. So since trees tend to be very similar, we use models to estimate volume, biomass, and carbon in trees based on measurement of certain variables, and models with those parameters as independent variables. We already talked about variables like diameter and height. Tree species also makes a difference, since the specific gravity of the wood on a green volume, dry weight basis is a function of species. We measure trees when they're live or green, and the biomass is calculated on a dry weight basis, which removes the effect of the weight of water in wood tissue. Specific gravity on a green volume dry weight basis over common species in the Northeast ranges from a low of 0.29 in northern white cedar to 0.66 in species like hickory, black locust, and serviceberry. This means that a cubic foot of oven dry solid wood, or the biomass of the wood, could weigh anywhere from 18 to 41 pounds. As an aside, we remove the effect of water since it's not biomass, and in a live tree, it can weigh as much as the wood itself in some species. And finally, estimating the coal content of the tree, or the reduction in the amount of volume or biomass due to rotten or missing in sections, is important as well. So we'll start with one of the more straightforward and widely used models called the Jenkins models. We'll work through sample calculations to estimate volume for a fairly average tree for Massachusetts that most of us could probably envision: a 16-inch diameter northern red oak tree, and one that is of average height for its diameter, about 73 feet tall. The Jenkins models are allometric, meaning they model the relationships between different parts of the tree. These models are developed as part of a meta-analysis. So the Jenkins study didn't go out and measure any trees themselves. What they did was they aggregated other studies of biomass across North America. These models use broad species groups, meaning that groups of species and genera have the same coefficients. These Jenkins models estimate total above ground biomass directly as a function of species and diameter at breast height, abbreviated DBH, 4.5 feet off the ground, which is where foresters measure trees. And so we'll start there. We use the diameter of the tree with this logarithmic model, and using the coefficients from red oak and converting the results from kilograms to pounds, we estimate that total above ground biomass is 2,431 pounds. In this case, to arrive at whole tree biomass, above and below ground biomass, I'm showing the calculation of the below ground or coarse root component, but the model form of any of the other components like foliage, the top, is all identical. A rule of thumb is generally that below ground tree coarse root biomass is typically on the order of 20% of above ground biomass. So we calculate the ratio, we multiply the above ground biomass times that ratio and arrive at the below ground biomass. We add them together to arrive at an estimate of 2,888 pounds of oven dry biomass for this tree. Now, these Jenkins models predict the mass of oven dry biomass, which conveniently for us, oven dry biomass is about 50% carbon. So we've got about 1,444 pounds of carbon in this tree. I mentioned earlier that carbon can be reported in different units. For a variety of reasons, carbon stocks are often reported with mixed units, metric tons for mass per US customary acre. So we need to convert from short tons to metric tons. A metric ton is equal to 1,000 kilograms, which turns out is fairly close to a short ton, or 2,204.6 pounds. We also often report carbon on the basis of the equivalent amount of carbon dioxide. Using chemistry, we can use the ratio of the molar mass of carbon dioxide to carbon. Carbon has an atomic mass of about 12.01 grams per mole, oxygen 15.99 grams per mole. Working through all the math leaves us with a ratio of mass of about 3 2/3 carbon dioxide to carbon. And we can put that all together to estimate that this tree has 2.4 metric tons of carbon dioxide equivalent using the Jenkins models. I talked about some unit confusion earlier. Many times when folks discuss forest carbon, they simply say carbon, but they might not express the units. You can see that short tons, 2,000 pounds, and metric tons, 2,204.6 pounds, are fairly close. But in other cases, people will express carbon in terms of carbon dioxide equivalent content, which results in a much different number. A clear idea of the units in which the estimates are expressed is crucial. Now, as simple as that model was, there are many other models out there. For example, the Forest Inventory and Analysis Program, which is the largest field-based inventory program in the country, and it functions as the country's forest census, uses what is called the component ratio method. This approach uses the ratio of biomass in the central stem, which is determined presumably using better localized models rather than national scale estimates, to biomass in the central stem is determined using the Jenkins method. The Jenkins method is then used to estimate the biomass in each component, and that ratio that I just mentioned is then used to adjust each component. To illustrate the flexibility of this approach, any volume estimate can be used. Here we see the form of different volume models used in different regions of the country. Some range from very simple, like here in the southern US, others are extremely complex. Volume, the point and place of beginning with this model, can be estimated with any of these models or others. Currently, biomass and carbon estimates from FIA within the 13-state area in the northeastern United States that includes Massachusetts uses the northern model that's shown here. This method starts with volume. Using the volume model for FIA's northeastern area, this tree has 39.5 cubic feet in its merchantable stem, inside bark in the bowl of the tree, the part of the tree from the top of a 1-foot tall stump to a 4-inch diameter outside bark top. These models assume that the tree is a perfect, intact solid, but trees aren't always perfect. Sometimes they're crooked or have pieces missing. We need to account for this missing material, which is called coal. There's two broad types of coal. One occurs as a result of historical utilization practices. It's called form coal. This happens when we need to take a round, straight log and turn it into boards. Anytime that log has sweep or crook, it can reduce the total potential amount of board volume sawn out of it. This is called form coal. Now, because the wood is still there and sound, we actually don't care about this type of coal as much for carbon accounting. The other type of coal is named rotten or missing coal. Sometimes this is obvious. The tree might be hollow. Other times it's more subtle, and the inventory staff in the woods needs to be out on the lookout for signs that parts of the tree might be rotten on the inside, like conchs or mushrooms coming out of the tree. This rotten or missing coal is the type that directly affects biomass and carbon estimates, since the wood fiber is missing or degraded. It's also the type of coal that's really hard to sense remotely, like from LiDAR or from space. For this example, though, to keep things simple, we'll assume there's no rotten or missing coal. The component ratio method at present uses nationwide average estimates of the bark volume as a proportion of wood volume and the specific gravity of wood and bark on a green volume dry weight basis to convert that estimated volume of solid wood to an estimate of dry biomass of wood and bark in the central stem. And in this case, we get a little bit over 1,700 pounds. Now, remember how I mentioned that the Jenkins models were embedded in the component ratio method? Next, we'd use those Jenkins models to estimate the biomass in that same part of the tree, the bole, and develop a ratio of estimates of the volumetric method to the Jenkins method. Using those allometric relationships from that Jenkins method, we determine the Jenkins-based estimates of biomass and the other components in which we're interested, the top excluding foliage, the below ground part, and the stump. Then we'd apply the ratio we developed in the last step to each of those components, effectively converting them from Jenkins estimates to volumetric estimates. And finally, we add them all up to get the estimate of total dry biomass in the tree, about 2,600 pounds. Now you might notice that we've been working with biomass on a dry weight basis. This is because, again, the water could amount to as much as the dried weight of the wood and bark fiber in a live tree. Dry weight densities are much more constant regionally and over time, between seasons and years. And again, dry weight is also convenient because dry tree biomass is almost 50% carbon. Using that ratio of dry biomass having approximately 50% carbon content results in an estimate of about 1,300 pounds of carbon for this tree. We'll do some dimensional analysis again and convert pounds to metric tons and carbon to carbon dioxide equivalent. And we can see that our 16-inch, 73-foot tall oak tree is estimated to contain about 2.16 metric tons of carbon dioxide equivalent. Now, this is about 10% less than the Jenkins models that we just reviewed first. So this is another important concept, that different equally peer-reviewed models and methods of estimating volume, biomass, and carbon of trees can produce estimates that vary, in this case 10%, but sometimes as little as 5 to more than 33%. So when comparing two independent estimates of forest carbon stocks in a tree or tract of land, knowing the modeling approach that was taken is very important. There are also some differences for standing dead trees that take into account the fact that they often have parts that fall off them as they decay, and that their density changes as they become subject to rot and decay. And to put these estimates in perspective, if we were to look at an average acre of forest land here in Massachusetts, using these component ratio method models, we might expect an average of 125 to 150 metric tons of carbon dioxide equivalent per acre in the above and below ground parts of standing live trees greater than 1 inch in diameter. The standing dead tree pool might be about 5% of that or so. And importantly, these two estimates are just for that example tree at a single point in time. If we look at growth and assume that this tree is growing at about 0.08 of an inch in diameter a year, which is about average in Massachusetts, that results in growth of half a cubic foot, 14.5 pounds of carbon, 50 pounds of carbon dioxide equivalent, or just over 2/100 of a ton of 2/100 of a metric ton of carbon dioxide equivalent per year on that single tree. Over an acre, we might see 0.5 to 2.5 metric tons per acre per year of growth on most undisturbed, well-stocked forest land. As I mentioned, there's other models we could use with different requirements. Here's a comparison of 4 approaches. We just reviewed the top 2, the Jenkins and component ratio methods, in depth, and there's at least a half dozen more. Just these 4 peer-reviewed, widely used models shown here result in a spread of, about 1/2 ton of dry biomass or 3/4 of a ton of carbon dioxide equivalent. So again, just because people talk about comparing estimates of carbon stocks doesn't mean it's automatically an appropriate comparison. Another consideration is that these are just estimates and subject to different types of error at every step of that implementation, including measurement, modeling, and sampling error. We might choose one model over another because they might let us measure fewer things at greater expense in the field, or because they could actually be more accurate and efficient than certain difficult measurements we might need to take on upper stem heights. The choice of sampling method is also important. Methods that select trees based on frequency will provide less statistically efficient estimates of biomass than those that select trees for sampling proportional to their diameter. The take-home message is that when someone starts talking about forest carbon, it's very important to understand the assumptions and methods behind their statements. To help put these estimates in perspective, under average usage assumptions, a light-duty non-commercial automobile emits about 5 1/3 metric tons of carbon dioxide per year. An acre of forest land might sequester between 1/2 and 3 metric tons of carbon dioxide per acre per year. And yards might sequester about 1/3 of a metric ton of carbon dioxide per acre per year. Now, measuring trees and developing models to estimate their volume and biomass, let alone smaller but equally important forest carbon pools like down woody debris and soils, could easily take up multiple lectures. So far, we've talked primarily about measuring stocks directly, and repeated measurements on the same individual trees or downed logs can help yield estimates of change or flux between those pools. Now, another technique that's used is the estimation of flux directly through the use of something called the eddy covariance method. In this method, towers are raised over a specific tract of forest land and equipped with instruments that measure air movement and the concentration of chemicals and gases, including oxygen, a byproduct of photosynthesis, and carbon dioxide, a byproduct of plant and decomposer respiration. Essentially, the amount of air moving at various heights in and above the forest canopy is measured, and then multiplied by the concentration of chemicals measured in those packets of air. And we can estimate masses of chemicals that are moving around in forest ecosystems. This helps estimate net ecosystem exchange at a much finer temporal resolution, say every 15 minutes or 30 minutes, than the methods that we just talked about. When combined with detailed measurements of plants and soils at the site where the tower is, we can see where carbon is accruing and depleting at the site to develop a very, very detailed understanding of a pretty small localized site. The final category of measurement methods I want to talk about are indirect methods. These include the use of remotely sensed data, like from a satellite, an airplane, a drone, or a ground-based scanner. With this category of methods, we collect information about a site, like measurements of the reflected spectra of light from leaves using Landsat, or elevation above ground, like through LiDAR, or even the texture contained within a photograph of a site. And then we compare it. We compare parts of that image to known field measurements, to areas where we've got very detailed field measurements. And then we extrapolate that relationship from the comparison to the entire image. We can even stack multiple data sets together to develop multi-dimensional predictors that hopefully perform better than any single data set on their own. These don't always have to include remote sensing data. These could be anything that influence forest growth, like slope, elevation, aspect, soil type, in combination with spectral and LiDAR information. As a quick example, let's take a look at how we could use LiDAR to quickly estimate above ground live tree biomass on a tract here in Northfield, Massachusetts that was relatively recently acquired by the state. In this tract, because it's been recently acquired and just changed ownership, we have limited field data. LiDAR is an acronym for light detection and ranging, and it's an active sensing method where a pulse from a laser is shot out from a device that very accurately measures its position in three-dimensional space. The time it takes for various reflections from that beam to come back to the device is measured and translated to distance from the sensor and therefore elevation above the ground and sea level. Multiple returns can even be detected if the beam is only partially reflected by the first object it hits. We start with our LiDAR point cloud and remove it to and denoise it to remove returns from birds, atmospheric scattering, and so on. At this stage of processing, the point cloud includes the effect of underlying terrain, landform, and surface features. Then we normalize it to remove the effect of landform and topography. What we're seeing here is effectively the height of the first return from that beam of light that's shot out from the sensor on the airplane. We can even pick out things like tree rows in fields in this agricultural town. Next, we develop a very detailed canopy height map based on subtracting the last return, the ground, from the first return. We then clip the point cloud and canopy height map to areas where we have detailed measurements of the trees and thus estimates of live tree biomass. We can compare measurements from those plots and individual trees in those plots to various characteristics of the LiDAR point cloud specific to those plots. Live tree biomass is very strongly related to the average height of trees as weighted by their cross-sectional area, also called basal area, as shown here in this graph in the upper left corner. While we can't really get a good sense of the tree's diameter in our forests from aerial LiDAR yet, it turns out that the 85th percentile of height of returns in a given space or pixel is very well correlated with basal area weighted height, as shown in the lower right corner here. So using the point cloud, we calculate the 85th percentile of height of returns above ground within a pixel size that's the same as our research plots. And then we use the relationship we developed that uses 85th percentile height to predict above ground live tree biomass. And we can map that and figure out which areas of that tract have more or less live tree biomass. So we've talked about some ways to measure and monitor forest carbon stocks specifically for trees. As we've seen from the relative size of different pools, trees are one of the larger pools and probably the most dynamic and easily manipulated, so it makes sense to focus on them. We can now talk a little bit more about those dynamics, how carbon changes over time at different scales, from trees to stands or groups of trees that are managed together to entire landscapes. Within Massachusetts at present, we can see that the patterns here of where tree biomass is stored within the various components of trees. Most biomass is stored in the tree boles. The top and below ground parts of trees are fairly comparable. There are some notable differences between hardwoods and softwoods. Deciduous and evergreen trees, like hardwoods, tend to have more biomass in their top, and softwoods tend to have more biomass in their foliage. Again, this makes sense if we stop and think about tree form and branching patterns and the relative nutrient composition between hardwood leaves and softwood needles. As trees change size too, these patterns of biomass distribution change. Here we can see how the proportion of biomass and carbon in different tree components varies as a function of species group and diameter. Again, sticking to the component ratio method, it's important to understand that saplings, trees between 1 and 5 inches in diameter, don't have component estimates aside from above and below ground biomass. So we expect a small discontinuity at 5 inches. Also, the component ratio method specifically excludes foliage. I'm including it on this chart as a point of reference, but it's important to note that it might be included in some Jenkins-based estimates of biomass and will be excluded from FIA's component ratio method-based approaches. And so foliage alone can account for a 5% difference in those estimates. At the tree level, one thing that can often be overlooked is the concept of cull. Larger trees, which tend to be older trees, on average have more rotten or missing cull. This makes sense in that those larger, older trees have been exposed to the elements and beat up by nature and their neighbors for longer. So they tend to have more root rot, cavities, damage where branches have died and fallen off or otherwise been broken off. And this is evident in inventory data. Here we're looking at data from hundreds of thousands of trees measured across the Northeast. Given basic characteristics of stand development and disturbance history, there are, of course, a larger sample size of smaller trees than larger ones. The mean tendency, though, based on this sample, is for rotten and missing coal to increase as diameter increases. Since tree diameter can stand in as a surrogate for tree age, we might be able to conclude that as trees age, they're more likely to have diminished biomass and carbon stocks relative to potentially perfect trees or other size or age classes of trees. So while an individual tree in perfect growing conditions without any competition might continue to have the potential to accrue large amounts of carbon at increasing rates over time, when considering just coal, realized biomass and carbon content are diminished relative to their full potential. Growth of individual trees in the absence of competition is also not indicative of stand dynamics. After a disturbance, stands are filled with tens of thousands of tiny seedlings per acre. Stands that are centuries old may only have tens or hundreds of large trees per acre. No stand can escape the basic principles of density-dependent mortality as those trees fight for growing resources. So while there's still an awful lot we have to learn about stand level dynamics and uneven aged forest management, actual data from the Forest Inventory and Analysis Program showing carbon stocks in different pools as a function of stand age certainly reinforce some of these basic concepts we're familiar with. This graph shows average carbon stocks in various pools as a function of stand age and oak hickory stands from across the Northeast. With respect to tree-based pools, volume and biomass start small and increase rapidly here as trees grow into pole timber and small saw timber. The volume growth on live trees far surpasses the mortality that occurs as a result of stem occlusion and competition. But at some point that varies for each stand based on site, competition, and a host of other factors, that accretion starts to diminish as decay, mortality, and disturbance catches up. These graphs also show the trends in carbon stocks in other pools. As we'd expect, carbon in live saplings peaks at a relatively young stand age and then gradually diminishes. Understory shrub carbon peaks even earlier on and then gradually diminishes as the stand ages. Carbon in standing dead trees gradually increases with stand age, as does carbon in dead and down wood on the forest floor. Carbon in litter and duff generally tend to increase. Disturbances tend to break up the canopy and allow sunlight to reach the forest floor, increasing temperatures there and accelerating decomposition. These pools usually build up in the absence of disturbance. One pool that's easy to overlook but is large in magnitude is soil organic carbon. FIA has taken measurements of that pool, but they are not over a very long time period yet, and they aren't very intensive in space. Soil organic carbon is highly variable and often different from site to site, but changes are commensurate with the scale and intensity of disturbance, as well as site and soil characteristics. For all but the most severe disturbances in coarsest soils, it tends to be replenished fairly quickly, on the order of a decade or two. For this graph, I'm showing soil organic carbon as a straight line here, since we don't have a lot of really strategic observations. Summing these pools, we can see that the signal from live trees really dominates the trends in total carbon over time. While uneven age stands are certainly more complex, each patch of trees of the same cohort or age might be reasonably expected to exhibit some of these same patterns on the scale of that patch. The stand's dynamics would reflect the pattern of age distribution in relative areas of each patch across the entire stand. The live tree pool is the most dynamic and easily manipulated. So if we break down the components of change for trees and look at net growth, which is the amount of carbon that's growing on existing trees called survivor growth, plus that in new trees called ingrowth, minus that in trees dying from natural causes called mortality, we arrive at net growth. We can plot observed net growth across the northeastern United States as a function of stand age, and we see that the mean response is one of early peaking, maintenance at moderate levels through the first century of growth, and then an asymptotic decline as maintenance respiration catches up with gross biological productivity. Another factor that affects carbon flux and stocks is site productivity. Not every acre of forest land is created equally. At an intuitive level, we probably readily grasp that mesic or floodplain soils might be more productive than excessively drained sites or thin, rocky soils up on top of a hill. Using actual observations from forest inventory and analysis, we can see that despite a bit of noise around the means and the trends, this is borne out. More highly productive sites typically accrue carbon at a faster rate, the slope of the line is greater, and to a higher maximum, the upper asymptote is higher than on less productive sites. Forest management can also affect carbon stocks. Here we've got a schematic graph showing examples of different forest carbon stocks under different management regimes. Unmanaged stands, shown in the dark green line, will always accrue the most biomass and thus carbon over a single rotation or stand lifetime. However, that biomass will be on many more trees relative to a managed stand, so the rate of growth of individual trees might be lower, and the quality of those trees may not be as suitable for end uses requiring larger stems or defect-free stems. Thinning trees in an even-aged management regime, shown by the lighter green line here, where most of the trees are the same age, sacrifices some total carbon storage in the woods by giving individual trees room to grow. Those individual trees are selected based on their vigor and ability to meet certain goals, maybe providing acorns for wildlife or the most highest valued forest products, but they grow quicker and to larger total size than under a no management regime. Less frequent, but larger magnitude disturbances tend to dominate these stands. You can see these even age regimes have a definite starting point and upper asymptote, in contrast to uneven age stands shown in shades of blue, where trees of all ages are intermixed in patches of different sizes. The uneven age stands can be managed at different densities for different tree sizes as needed to meet different goals. More frequent, but smaller magnitude disturbances are more common in uneven age management regimes. We can scale these patterns up from individual stands to entire forests and landscapes. If an entire forest was subjected to similar social pressures and historical patterns of use, it might be largely even-aged, and patterns of growth and yield at the landscape scale would look like the even-aged curve. This isn't necessarily desirable from the perspective of a robust forest resilient to disturbances or stressors. Having different stands at various stages of development within a forest or landscape creates patterns of growth and yield at that scale more akin to the uneven age patterns. One thing that's common to both regimes is that they're systems of dynamic equilibrium. A change from one state to another, for example, managing an uneven age landscape from a lower to a higher average level of stocking, results in more stored carbon in the forest at the expense of the rate of growth and carbon accrual on trees. Similarly, managing a largely even-age landscape that's relatively highly stocked and growing slowly to a condition that's more sparsely stocked but grows and sequesters carbon from the atmosphere faster might require a net release of carbon from forest ecosystem stocks. And in fact, this even-age pattern is evident in our forests in Massachusetts. On our state forests here in Massachusetts, we have detailed long-term information on stand age collected since the 1960s. Much of DCR's land was acquired after agricultural abandonment in southern New England, when railroads and the Industrial Revolution led to widespread settlement of much more productive and more easily farmed land in the Ohio and Mississippi River valleys and plain states. This, coupled with relatively low management levels that led to this age class distribution working its way through time. At present, over 80% of the agency's lands are estimated to be in stands that are in a narrow age range from 70 to 120 years old. This pattern is evident statewide as well. If we recall the patterns of stand development with respect to carbon stocks, we'd probably readily recognize that this is at an age when we might expect rates of net carbon accrual to decline simply due to basic biology and intrinsic stand dynamics. So these patterns associated with an aging forest are indeed becoming more obvious in inventory data. We only have long-term data dating back to the 1950s for a subset of our forest land called timberland, And measurements from those earliest inventories were provided in terms of cubic feet, as shown on this graph, not biomass or carbon. But the basic trends, now that we know how to convert cubic feet to biomass, are very similar. We can see declining patterns of gross growth and ingrowth, increasing mortality, and declining harvest levels as Massachusetts has become more suburbanized and shifted from a manufacturing to a technology-driven economy. And compared to other states in New England and New York, Massachusetts has very high stocking levels, middling growth rates, well above average mortality, and extremely low rates of harvesting. How does this bode for our ability to store more carbon and diversify our forests? So there are certainly examples of what can happen when we start to think about these trade-offs between forest carbon and other ecosystem services. Let's take a look at a few. The 1938 hurricane tore through central New England in September of that year. The landscape consisted of recently abandoned agricultural fields dominated by eastern white pine with a very lumped age class distribution, just as now. The hurricane, as tragic as it was, created an incredible natural experiment. The hurricane caused extensive damage in the upper Connecticut River watershed, which happened to have a stream gauge right in Turner's Falls, but virtually no damage in the Androscoggin River watershed up in Maine. Both watersheds had similar patterns of land use and forest growth. Plotting the cumulative summer flows from the two watersheds against each other, from the seasons when we would expect to see the most evapotranspirative demand from the growing trees, shows a very large anomaly after the hurricane. The net effect is that the huge swaths of devastated trees, which were of a single age class without many young replacement trees to help take their place, could no longer slow and filter the rainfall after the hurricane. So precipitation during the summer months found its way quickly into streams and rivers in the heavily damaged Connecticut River watershed, carrying with it soil and nutrients, while flows within the undamaged Androscoggin River watershed remained largely as normal. Now, this was a non-controlled experiment, so it's impossible to say for sure whether better forest management or a forest comprising stands of a wider range of ages and species would have helped mitigate that damage. But are there any lessons we can apply to our forests now? I mean, certainly there may have been a more diverse mix of tree species now, but in terms of ages, maybe there wasn't that much difference. If these types of hurricanes have a 1% chance of affecting our area in any year, could our forests as they exist now cope with that damage? Would we have enough young trees to keep taking up nutrients and water to prevent severe water quality effects as older trees were mauled and toppled by that wind? What about other invasive pests and pathogens that are affecting our forests now? Another example is fire risk. We may not think of our forests in Massachusetts as being as vulnerable to fires as in the Western United States, but we do have extensive areas of pitch pine and scrub oak barrens in southeastern Massachusetts. These ecological communities are globally rare, harbor numerous threatened and endangered plant and animal species, and are dependent upon fire for management and survival. Many of these habitat types are near extensively developed neighborhoods on the mainland and islands in Massachusetts, and these forest types are extremely flammable. Decades of fire suppression efforts have allowed for trees and shrubs to grow far beyond what would be naturally maintained under a regime of low, frequent fire. This allowed these forest types to sequester and store vast amounts of carbon. These ecological communities, in their natural condition, would look more like this. That's quite a difference, isn't it? So while we could use forests to store more carbon, that would carry a certain amount of catastrophic risk. By managing them at a lower level of stocking, and this is certainly an extreme end of that example, and periodically using certain types of treatments to remove carbon, we can manage them in a far more sustainable fashion, sequester carbon, and not be as subject to those catastrophic periodic losses. So forest management comes with many trade-offs. Our forests in Massachusetts now are largely even-aged, and current stocking levels are more or less at the location of this star here on the graph. With these classic biological growth curves, maximizing the rate of production, or in this case, carbon sequestration, occurs at where average annual growth, called mean annual increment, or MAI, is maximized. We would harvest all the trees and start over and sequester all that harvested carbon somewhere. This occurs later than instantaneous production, maximum rate of change, and certainly later than maximization of rate of increase of stocks, shown by these various percentages here. With just two considerations, keeping carbon stocks in the woods and maximizing carbon flux, or how fast it's pulled out of the atmosphere, we're forced to choose. By allowing stocking in the forest to increase, we're sacrificing how fast we pull it out of the atmosphere. Similarly, we could harvest a bit more and release some carbon stocks in the woods, but pull it out of the atmosphere a little bit faster. When we're performing carbon accounting, choosing a starting and ending point for our accounting is entirely arbitrary. By evaluating changes to carbon stocks and emissions relative to our current stocking level and disallowing emissions, we're implicitly stating that we believe our current stocking level is good. But is it? Do we have much more room in our forest to store carbon? Is our current level of mortality, tied for second place in New England, good? If we were to select a single stand as the level of analysis with current average stocking and say that we need to minimize emissions, that would lead to a decision of no harvesting, especially over a short time frame, because our stands could never grow again and recoup those lost stocks as fast. If that analysis were repeated across many stands over a landscape, then we'd reduce the level of forest management, but at the expense of other non-carbon benefits like forest diversity and resilience. By only considering carbon, we ignore many other co-benefits like clean water and habitat. And again, this reinforces the point that the wrong scale of analysis, either in space or time, can lead to incorrect results. And to reinforce the notion that forest management must look at long-term time horizons, forest management can easily recoup carbon debt over multiple management periods. But by making the analytical window too short or choosing a different starting place, we might be foregoing many benefits, the least of which would be longer-term rates of sequestration. We still use forest products. We still need to provide habitat for the animals we're displacing. This particular example from the Pacific Northwest shows trends of carbon in different ecosystem and harvested wood product pools over time. And for an unmanaged stand in this dashed green line here, and under a managed stand with the various pools shown in different colors. Timber harvesting in a managed stand can store more total carbon than a non-managed stand. But by evaluating results over too short a time frame, less than one management cycle, we'd reach an incorrect result. Both types of stands, managed and unmanaged, are equally important, but for different reasons. Managing for forest carbon is far more complex than just maximizing the carbon stored in trees in the forest in the short term. So in closing, I hope this was a helpful introduction for people and the discussion about measurement and management of the forest carbon stocks were useful. I'm happy now to take any questions or talk more about any particular points.
This of you. Wow, thank you. Our attendee, Wendell, is here. Would you like to come up and be a panelist too and ask some questions, Wendell? You could put something in the chat so I know to do that. Here I thought all you had to do was measure the DBH and the height of the tree and you'd know. A lot more to it though, huh? Though maybe a good start for teams that were interested in trying to evaluate how much carbon is stored on a piece of property near their school. Are there tools that sort of an average citizen can use to try to figure out without being too complicated? I mean, this is fascinating, and there are so many caveats and deviations on how to calculate it. But I'm wondering if there's a simple version maybe that we could think about.
Yeah, so those Jenkins models that I mentioned are a great point in place of beginning. I think it's important to just remember that the estimates that you would generate using those Jenkins models wouldn't be directly comparable to estimates that are readily available from, say, the Forest Service, because they use the component ratio method right now. So that's not necessarily good or bad, but you might conclude that
I think you froze. Here we go.
All right. The papers, the methodology is all in the public domain. Depending on the timeline and the needs, what I could do is I could round up the papers and set up for perhaps a sample spreadsheet with some calculations, if that would be helpful, where you could just plug in the DBH, the species and the diameter, and it would spit out the Jenkins-based estimates of the different components, if that would be useful.
I think that could be really cool to just to get an idea, and then to compare, measuring a site that's more softwoods or hardwoods, just to actually get hands-on numbers for a team. I think that could be really cool, and it would be a great way to practice measuring DBH, which is one of the things I know Felicia wants them to be able to do. Wendell has a question for you. He said that his town is considering clearing 10 acres of undisturbed woodland, about 100 years old probably, to create farmland. What kind of effect would that have on carbon sequestration?
So looking at the carbon benefits and trade-offs, I would imagine that those 10 acres of forest land have some carbon tied up in the vegetation and in the soil, to the extent that during the clearing, the wood in the stems of the trees could be used for the best quality, longest lived wood products they could, turned into furniture and flooring and construction products and things like that, as opposed to just chipped and taken to a dump or used for landscape cover. That would retain as much of those carbon stocks. It would tie up. It would store that carbon for as long as possible, and minimize some of the impact of the vegetation removal. Tilling the soil is likely to cause release of carbon from the soil pools as well. And you mentioned a farm. I'm not sure what type of agriculture, but there would be an effect there as well. I don't want to necessarily say impact, because again, there's certainly some kind of benefit to getting our having local farming as well. So to the extent that sustainable agricultural practices could be used, that system, those 10 acres, would reach a new state of dynamic equilibrium. There would be some release, there would be some changes during that state of change, but then once it was in agricultural use, there would be certain practices that could be put into place to build certain carbon stores back up. Low till, no till, making sure you left buffers around, riparian areas, minimizing erosion, things like that would all help. So there would be an effect, yes, but measuring the carbon content in the trees, figuring out if you could measure the carbon in the soil. There could be some lost sequestration potential. The amount of carbon that an acre of farmland could pull out of the atmosphere each year is likely probably less than an acre of forest land, but it all depends. And certainly that older forest land is likely not sequestering, it's not pulling carbon out of the atmosphere as fast as a younger forest. So what potential rate of sequestration, what's the foregone sequestration? Is it as it was as a 100-year-old forest? Is it as a 30-year-old forest when it's growing as rapidly as it could be? So again, kind of what is versus what could be are two very different questions.
Thank you. That was a a very interesting perspective on this. And I'm sure that our teams will investigate what's happening in their community in terms of this. Terrific. Well, thank you so much for your time, effort, energy, and expertise this evening. Really appreciated learning from you, and look forward to sharing this with our teams.
Yeah. One thing I would suggest is that our other programs within the state, I'm just talking to Wendell's comment here about a forestry plan. There's a service forester named Michael Downey. I could arrange to get the contact info to Britta, and Michael works very closely with a lot of municipalities on municipal forest land and even agroforestry. That's an interest of his. So if it was at all useful, I could get that contact information and maybe stimulate a discussion on that front. And at some point within the next several weeks, I could definitely get those papers together on the Jenkins methodology, so you could see the derivation of those coefficients and a spreadsheet that looked up those coefficients and calculated biomass, if that time frame would be about right.
I think that would be fabulous if you had time to do it. We would really appreciate that.
Absolutely. So happy to do it.
Excellent. Thank you. Thank you so much. And really, hooray! This Envirothon network of expertise is really pretty incredible. Well, have a great evening. I'm gonna